Welcome back to another lecture in my space robotics course. Here's what we're aiming for in this session. You'll learn how to design and evaluate a space operations concept by understanding when operators are needed, how operations is structured, and what tools support effective mission execution. This foundation will help you think more critically about the role of an operator, planning, and human-robot teaming in future missions. While every space robotic mission has had at least some level of human-operator interaction, we should expect when human involvement is critical. A good example of human operators playing a crucial role comes from the Spirit rover in 2004, seen here in its time of need. About 20 sols into the mission, Spirit stopped transmitting data entirely. Initially, teams suspected a hardware failure, but after reviewing its recent behavior, they noticed it had begun generating and transmitting an unusually large volume of data. Engineers hypothesized a flash memory fault was causing the rover to reboot repeatedly. They sent a command to bypass flash storage and boot into RAM only, a non-standard mode, and that worked. Spirit came back online and ultimately operated for over 6 years. This case illustrates that even in robotic systems with significant autonomy, human flexibility and systems-level reasoning remain essential, especially when diagnostic tools are limited. Despite the critical role that human operators can play, humans can also delay mission operations and experience cognitive fatigue. For example, during the early weeks of the Spirit and Opportunity missions, NASA operators at JPL worked on Mars time, shifting their schedules by about 40 minutes each day to stay aligned with each Martian sol. It worked well at first, but over time it started to break down. People were effectively changing time zones every day. Within weeks, they were exhausted. Reports of sleep loss, cognitive fatigue, and scheduling confusion started to pile up. Teams began missing uplink windows, struggling to prioritize science activities, and making decisions under pressure while sleep-deprived. NASA eventually scaled back the Mars time requirement to protect team health and planning quality. It's a good reminder that even in robotic missions, human limits, not just technical ones, can shape the mission's performance envelope. This grueling experience is no secret, as can be seen from this seminar flyer entitled Surviving Mars Rover Operations for Over 10 Years from the Mission Operations and Senior Staff Scientist Megan Wu. Even in highly autonomous missions, there are critical moments where we still need human operators in the loop. First, for complex science decisions like where to direct sampling or what surface features to prioritize. On the left, you see Perseverance's traverse across Jezero Crater, where scientists routinely plan on the fly to pursue emerging targets like carbonate outcrops or sediment layers. Second, we need operators for ambiguous terrain and unanticipated events. The image on the right shows Curiosity near Vera Rubin Ridge, where it got partially stuck in a sand trap. These aren't situations a robot can fully anticipate. They require human judgment to interpret conditions and adjust strategy. And third, for safety oversight, especially when there's risk to the robot or eventually a crew. Whether it's navigating steep slopes, mechanical failures, or power limits, humans are essential for monitoring and intervening when autonomy alone isn't enough. There are also times when we can't rely on operators, no matter how capable they are. During entry, descent, and landing, like in the 7 minutes of terror, there's simply no time to wait for input. The rover is descending toward the ground due for collision at hypersonic speeds, and the Earth is minutes away in light time. Autonomy is the only option. Bandwidth is also another constraint. Mars rovers depend on short relay windows to send data back through orbiters. Often, operators have to plan the next sol before they've even seen the results of the last sol. That's why autonomy and predictive planning are so critical in constrained communications environments. The robot often has to make the last call. This slide introduces the idea of an operations architecture, the system of elements that allow a mission to function effectively. It includes both human and robotic components and how they interact through interfaces and communication pathways. First, there are crew roles, whether it's engineers working on a surface team, operators driving cameras and tools, or planners reviewing science targets. These roles interface with mission control centers, places like JPL for Mars surface missions or Mission Control Houston for ISS operations. These centers coordinate across time zones, teams, and mission phases. All that relies on communication paths, including high-gain antennas, the Deep Space Network, or relay satellites like Mars Odyssey. These links define what data can be sent, how fast, and how often. They also determine how responsive the system can be. Finally, there are the onboard robotic systems, everything from Mars rovers to robotic arms, Astrobee on the ISS, or eventually mobile assistants on the lunar surface. Together, these components define how a robotic space mission actually operates, not just in principle, but day to day. Now that we've mapped out the components of a mission architecture, the humans, robots, and communication links, let's take a closer look at what actually flows through that system. This diagram shows the mirror operations loop, from Earth-based mission teams to the Deep Space Network to the rover on Mars and back. It helps to define what we mean by a singular robotic operation, one closed cycle of command, execution, and response. On the uplink side, we send a command sequence that could be anything from driving a few meters to executing a sample collection. Along with that, we include a timing window, and we define the mode of execution, whether it should run autonomously, be supervised, or wait for human intervention. On the downlink side, we need the essentials, status and health checks to confirm the rover is still functional, telemetry to verify execution, and often some position or sensor readout to evaluate results. On top of that, there's often a layer of nice-to-have data. Full resolution imagery, environmental context, and instrument logs, things that enrich science and planning, but aren't always necessary to close the operational loop. The basic flow of what's uplinked and downlinked defines the rhythm of planetary missions, and it also shapes how we prioritize bandwidth and time. In the next section, we'll look at the tools that help operators make these decisions in real time. This slide highlights the role of strategic planning, which is all about managing long horizon goals, decisions made well in advance, often with incomplete information that shape the mission at a systems level. On the left here is the Mars Sample Return Mission Concept of Operations. It's a great example of strategic planning in action, from setting a high-level mission objective like sample caching to coordinating multiple launches, landings, and rendezvous events. Each of these steps have to be sequenced precisely, sometimes years apart, with tight dependencies between spacecraft and systems. The bottom image shows Perseverance's traverse through Jezero Crater with markers for cache sample sites. These traverse arcs are planned weeks or months in advance, taking into account science priorities, terrain navigability, and available energy. Strategic decisions here define where the rover is going and why, long before tactical planning decides what the rover does on any given sol. The top right diagram illustrates downlink scheduling using the Deep Space Network. This is a global resource shared by many missions, so strategic planning involves securing communication windows to send and receive data. If your downlink timing doesn't align with critical activities like returning imaging, telemetry, or science results, it can create delays that ripple through the rest of the plan. Together, these examples show that strategic planning operates across spacecraft, time, and teams. It enables robotic systems to carry out complex missions in environments where real-time reactivity isn't always possible. This slide focuses on tactical planning, the short-term side of operations. These are day-to-day, hour-by-hour decisions that drive what a rover does next. On the left here is a timeline from the Mars Exploration Rover mission, showing how each sol's tactical process unfolded. This included science planning meetings, engineering assessments, command sequence development, all constrained by orbital pass windows and data availability. These cycles repeat daily, often under tight turnarounds. The operations team got to work when Spirit and Opportunity were asleep, which happens right about here, and had to map strategic plans to tactical plans within the sleep cycle in time for the rover to wake up with plans uploaded, which is over here in the timeline. Unlike strategic planning, which sets big picture goals, tactical planning responds to what actually happened, what the rover saw, measured, or encountered. For example, if a hazard was detected or a science target turned out to be more interesting than expected, the tactical team would pivot and adapt the plan. On the top right over here, you see an example of that kind of reaction. That is a mini TES data, a mineralogy measurement, overlaid on a navigation camera image. Tactical teams use overlays like this to quickly identify interesting spatial features and decide whether to direct the rover to investigate further. At the bottom right is an interface tool used to analyze those data products. Here, a data cube with spectral skewers give insight into the material composition of a specific rock. These visual tools allow scientists and operators to assess science value fast and fold that into the next SOLS plan. So overall, tactical planning is about working with the constraints of time, data, and communications to make effective short-term decisions grounded in the actual state of the vehicle and its surroundings. Now that we've looked at operational architectures and planning frameworks, we're going to shift toward thinking about operational fit. How do we map specific mission tasks to the right in mode of execution? Not every task should be handled the same way. Some are best done by a human in the loop through teleoperation. Others can be handled more efficiently through automatic routines or with varying degrees of autonomy. The question at the center of this slide is, how do we decide? What makes one task a candidate for full autonomy and another one better suited for supervised control or scripted execution? In the next few slides, we'll walk through some criteria and examples to help make those decisions more structured and justifiable. One of the most critical factors in deciding how to operate a robotic system is latency tolerance. Basically, how well a task can handle a delay between command and response. This image here, you should be familiar with it, shows the one-way light time from Earth to various destinations in our solar system, from just over a second at the moon to over 6 hours for the outer Kuiper belt. At these scales, real-time control becomes impossible, especially for anything beyond Earth orbit or cislunar space. For example, Mars has a latency of 4 to 22 minutes one way, meaning a round-trip command and response loop could take nearly 45 minutes. So for time-sensitive tasks like hazard avoidance during descent or precision sampling on a moving surface, you can't wait for operator input. The system needs to handle it autonomously, or at least semi-autonomously. Latency defines not just how we communicate, but what modes of operation are even viable. Another key decision factor is science value sensitivity. How much is at stake scientifically if a decision is wrong or suboptimal? The image on the top right shows the annotated panorama of Perseverance's sample depot, where each of the cache sample tubes is carefully placed and documented. These tubes represent finite, high-stakes decisions. We can only bring back a small number of them, and each sample costs tens of millions of dollars to collect, transport, and eventually return to Earth. Because of how expensive, we don't want those decisions made blindly or purely algorithmically. Robots don't have the contextual judgments that a team of planetary scientists, geochemists, and mission planners can bring. That's why for high-sensitivity science tasks, like deciding what to sample or what to leave behind, we often keep humans in the loop. The stakes are too high to leave that entirely to autonomy, especially when scientific insight may come from interpreting subtle context that a rover doesn't recognize. Another important factor in choosing how to operate a robotic system is fault recovery. What happens when something goes wrong, and who or what has the ability to respond. Earlier, we talked about the Spirit flash memory crisis, where the rover went into the endless reboot loop after overloading its file system. This situation couldn't be fixed autonomously. Recovery required human reasoning, pattern recognition, and a pretty creative workaround from the engineers on the ground. A more recent and representative example comes from Curiosity in 2016, when it entered safe mode due to a software mismatch between a routine file update. You can see the humor in this tweet on the right, robot code for hungover, but it points to something real. The rover's onboard fault protection was smart enough to stop what it was doing and protect itself, but it couldn't resolve the problem. That still required human engineers to dig through logs, diagnose the root cause, and send a software patch. So when we're deciding whether a task should be fully autonomous or include humans in the loop, one of the key questions is, if it fails, can the robot fix it? And if not, how long would it take for a human team to diagnose and intervene, assuming that communication is even available? Fault recovery isn't just about safety, it's about mission resilience. The less recoverable a task is on board, the more likely we are to assign it to a mode that includes human oversight. Some faults, like getting a nonsensical reading, are pretty easy to handle automatically. A nonsensical sensor reading fault is easy to detect, such as checking if the sensor readings are within an expected range, and easy to correct for, such as rejecting that measurement and querying another sensor measurement. The last key factor we'll look at is a robot's state awareness capability, how well a system understands both its environment and its own condition. On the left, you'll see Perseverance's AutoNav system in action. This capability allows the rover to process 3D terrain, detect obstacles, evaluate traversability, and plan safe paths, all on board without waiting for ground commands. That level of awareness supports fully autonomous driving across complex terrain. In contrast, on the right is the Phoenix Lander's soil handling arm. While it could move and dig on command, it had limited sensing of what it was interacting with, no force feedback or soil contact sensors. It couldn't tell if it had actually collected a sample. That meant humans had to visually confirm success from camera images and command corrections if the arm missed. One important implication of low state awareness is that the system often has to downlink a lot of supporting data, images, health status, sensor logs, for humans to interpret what happened. That places a burden on data bandwidth and planning, especially when communication windows are short. So when a robot has low state awareness, we usually default to teleoperation or tight supervision. But if a system can perceive its context and respond intelligently, we're more comfortable assigning it higher autonomy. Let's bring back together what we've discussed so far into a practical decision-making guide. This table shows how to map different task types to their most appropriate operations type, ranging from teleoperation to full autonomy. First, for tasks involving complex decision-making, we keep humans closely involved. An example is science target prioritization, like the Perseverance rover sample tube collection in Jezero Crater. With a limited number of samples that can return to Earth, the mission demands expert scientific judgment. Next, we have hazard-sensitive tasks. This typically involves situations with significant mission risk. For instance, think about the robotic arms aboard spacecraft, like the ISS's Canadarm2. Activities such as grappling incoming cargo vehicles require close human supervision to ensure nothing critical is damaged. For tasks that are predictable but time-sensitive, semi-autonomous operation is ideal. Remember the Curiosity rover's drilling operations? It knows the routine and can manage steps on its own, but still relies on human supervision for safety checks or to handle unexpected rock hardness. Finally, simple and repetitive tasks like rover wheel odometry tracking or routine system health checks are perfect for full autonomy. Consider the Perseverance rover's AutoNav, which autonomously manages its routine driving, adjusting paths quickly without human input. By understanding and evaluating the factors that we've covered, latency, science value sensitivity, fault recovery, and state awareness capabilities, we can choose the right balance between autonomy and human oversight to assure mission success. To close out, let's talk briefly about what makes a good operations tool, especially from a human-computer interaction perspective. The image you see here is the Science Activity Planner, or SAP, used during the Mars Exploration Rover missions. It supported everything from planning traverses to selecting science targets. First, good tools need visual clarity. Teams need to quickly understand timelines, spatial plans, and data priorities at a glance, especially when bandwidth or decision time is limited. Second, they need to support shared mental models. Everyone, scientists, engineers, mission planners, should be able to look at the same interface and understand what the plan is, what the robot is doing, and what still needs to happen. And finally, tools must support efficient replanning. In real missions, things change constantly. Data arrives late, systems fault, or science opportunities emerge. Good interfaces help teams pivot quickly without starting from scratch. Designing for human-robot operations isn't just about autonomy. It's about building tools that let humans and robots collaborate effectively under constraints. To wrap up, everything we covered today ties back to this goal. You now have a framework for thinking about when operators are essential, how space operations are architected and planned, and what tools enable better mission outcomes. These are the key ingredients in building and assessing a robust space operations concept.